everybody. Today we are first going to discuss this question. It says that show that the polar of any point on the circle x square plus y square minus twice ax minus 3a square is equal to 0 with respect to another circle x square plus y square plus twice ax minus 3a square is equal to 0 will touch the parabola y square minus 4ax. So we will have to consider a point on this first circle, and the polar of such point with respect to the second circle, we shall have to show that the polar of that point with respect to the second circle will touch this kind of parabola y square is equal to minus 4x. Show that the polar of any point on the circle x square plus y square minus twice ax minus 3a square is equal to 0 with respect to this second circle x square plus y square plus twice ax minus 3a square is equal to 0 will touch the parabola y square is equal to minus 4x. So you have to show this result. Okay, so how to prove this result? Let us first write these two given circles. These are the first and second circles. And suppose P alpha comma beta is a point on the first circle, circle number 1. Therefore, the coordinates of the point P must satisfy the equation number 1. Got it? This first equation. And therefore, we shall have this result alpha square plus beta square minus twice a alpha minus 3 a square is equal to 0. So we have this equation number 3. Okay. Now, as per the question, we will have to find out the polar. We will have to show that the polar of this point P with respect to the second circle. Okay. Polar of this point P with respect to this second circle. So with respect to the second circle, that means we shall have to consider this curve as the curve S is equal to 0. Got it? And with respect to this curve S is equal to 0, this second circle, we have to find out the polar. We know that the equation of the polar is t is equal to 0. Okay, this is the expression of t. T is equal to 0 evaluated at the point alpha comma beta. So the equation was x square plus y square. So what should be t? T should be x into alpha. In place of x square, we shall have x into alpha plus in place of y square, we shall have y into beta. So x into alpha plus y into beta. This is the expression x into alpha plus y into beta plus in place of twice x. In place of twice x, we will have to replace this twice x by x plus alpha. So we have replaced this twice x by x plus alpha and we get this expression a into x plus alpha minus the constant term minus this 3a square term is there. So we are just subtracting this term minus 3a square and that is equal to 0 over here. So this is the expression of the polar of the point P with respect to this circle number 2. Got it? And we are converting this expression of the polar in terms of the standard equation of a straight line y is equal to mx plus c. In that case, dividing this total expression by the coefficient of y. Coefficient of y means over here beta is the coefficient of y, but it is beta is the coefficient of y. So dividing the total expression by beta, we get that coefficient of x would become is equal to m is equal to minus alpha by a into beta, and the remaining constant term would be is equal to 3a square minus a alpha divided by beta. I am not showing the detailed computation. It is directly follows from the result that by dividing by beta we get this kind of expression. Y m is equal to this and c is equal to this kind of result. Now the condition. Initially when we had the result that y square is equal to 4ax, 4ax. If this is the equation of the parabola, then we know that y is equal to mx plus c. This kind of straight line would touch this kind of parabola if c is equal to a by m. I proved this result in my last lecture. C is equal to a by m. But in this question, in place of y square is equal to 4ax, in place of y square is equal to 4ax, we have minus 4ax. Okay, y square is equal to minus 4ax. So a negative sign is to be introduced over here. So minus 4ax. That means a should be replaced by minus. So the condition would be c is equal to minus a by m. And if c is equal to minus a by m, in that case, c plus a by m, this expression should be equal to 0. Got it? This expression should be equal to 0. That's why we computed this expression by putting the value of c and m. We finally computed this expression, and ultimately I am not going through this calculation because these are the simple algebraic calculations. By taking LCM, we finally get this type of result. And if you observe the final line, this line, if you observe the final line, we have alpha square plus beta square minus 3 a square minus twice a alpha. And what is this? This is actually nothing but this result equation number 3. This is the equation number 3. Alpha square plus beta square minus twice a alpha minus 3a squared. So by this relation number 3, this total expression becomes is equal to 0. That means we can now say that c is equal to minus a by m. This condition is satisfied. And as because it is satisfied, therefore we can say that this equation y is equal to mx plus c, this equation will touch the parabola y square is equal to minus 4ax. Got it? Therefore, we finally get this kind of conclusion that the straight line will touch the parabola y square is equal to minus 4ax. This kind of question may come in exam, and it may have about 5 or 6 marks in exam. So this is one problem that I wanted to discuss. And suppose we discuss one more problem. Find the condition that the two straight lines Lx plus L1x plus M1y is equal to 1, and this kind of second straight line L2x plus M2y is equal to 1 will be conjugate with respect to a conic. You see, this is a given conic. This may be a parabola, even maybe a hyperbola, even maybe an ellipse, any other conic may be there. So two conjugate lines means the pole of first line will lie on the second line, and if it is so, in that case we know that pole of second line will lie on the first line, and this kind of lines are called conjugate lines with respect to this kind of conic. So in such examples, what we need to prove? We need to prove that pole of one straight line lies on the second straight line, and in that case obviously it means that pole of second straight line will lie on the first straight line, and in that case of course these two straight lines are conjugate to each other. So this much we will have to prove. Got it? So let's see whether I have any ready-made solution for this or not. Let me check. Just a minute. Oh yeah, I already have this one. This is the question. Luckily I got it. Anyway, so what is the question? The question says that find the condition that two straight lines L1x plus M1y and L2x plus M2y will be conjugate with respect to the conic ax square plus twice h xy plus by square is equal to 1. It may be any other point. So let's start the solution. This is the given conic ax square plus twice h xy plus by square is equal to 1. And given straight lines are these two straight lines, L1x plus M1y is equal to 1 and L2x plus M2y is equal to 1. These are two given straight lines. Now what we'll have to prove? We'll have to prove that the pole of first straight line lies on the second, and therefore in that case pole of second straight line will obviously lie on the first straight line. These are all known results. So we start with a point P, alpha comma beta, and suppose that this point P be a pole of the straight line number 2. P is the pole of the straight line number 2. And if it is so, in that case, the straight line number 2, sorry, number 2, this number 2, is in that case, this straight line number 2 must be the polar of this point P with respect to this circle with respect to this conic number 1. This equation number 2 must be the polar of this point P with respect to the conic number 1. Or in other words, we can again you see we have a formula that t is equal to 0. This formula t is equal to 0 is the polar of a point with respect to a conic. So we know the point, we know the conic, so we can apply the formula t is equal to 0, and then by this formula we will be able to find out the equation of the polar line, and that polar line would nothing but this line number 3, because we assumed that this point P is the pole of the line number 3. Therefore this line number 3 must have this kind of equation, this kind of format, t is equal to 0. Okay, and so from this formula t is equal to 0 applied on this point P, we get the equation of the polar of this point P with respect to the conic number 1. This is the conic S is equal to 0. This is the conic S. This is the expression of S. So if this is the expression of S, then what would be the expression of T? Then the expression of T would be, in place of ax square, we will have the result alpha, ax alpha. In place of the expression ax square should be replaced by x into alpha. This y square should be replaced by y into beta, and twice xy should be replaced by h into x beta plus y alpha. Twice xy is to be replaced by h beta plus y alpha. So this would be the equation of the equation of the polar line of the point P. But as per our assumption, what did we assume? We assume that this point P is the pole of this equation number 2, or this equation number 2 is the polar of this point P. That was our assumption. But from the standard formula t is equal to 0, we computed that this is the polar line of the point P with respect to this conic number 1. And therefore this straight line and this straight line, both of these two straight lines are representing same polar line. Both of these two straight lines are representing same polar line of this point P with respect to this conic 1. So equation number 2, this equation number 2 and this equation, both of these two equations must be identical to each other, as because they represent same straight line. Therefore, these two straight lines, this straight line number 2 and this straight line, this must be identical to each other. Got it? And therefore, as because they are identical to each other, therefore we can compare this line and this line. Compare means we can compare the similar expressions. For example, over here the coefficient of x divided by coefficient of x. Over here the coefficient of x is equal to alpha a alpha plus h beta, and over here the coefficient of x is equal to L1. Therefore we can compare this two ratio a alpha by plus h beta divided by L1. The coefficient of y over here is h alpha plus b beta. This is the coefficient of y, and over here the coefficient of y is equal to m1. Therefore, you can compare these two expressions, h alpha plus b beta divided by m1. And on the right hand side we have we have 1. On the right hand side we have 1, and we have 1 over here as well. Therefore, you can write 1 by 1. So if we compare these two ratio, first ratio with the third ratio, compare these two, we will get one relation. This is a relation involving the quantities alpha and beta, and this is another relation comparing the second ratio and the third ratio. This would be another relation involving alpha and beta. So we actually have two unknown quantities involving two relations, two linear relations involving two unknown quantities. So by cross multiplication, we can compute the expression of alpha and beta. We can compute the expression of alpha and beta. Got it? So in this way, we found the coordinates of the point P. Okay, in this way, we found the coordinates of the point P. And in order to show that these two straight lines, or these straight lines number 2 and 3, this straight line number 2 and 3, in order to show that these two straight lines are conjugate to each other, we will have to show that the polar of first line lies on the second line. That means polar of the first line means P. This P alpha comma beta lies on this second line, or in other words we can say that the coordinates of the point P must satisfy this equation number 3. Okay, coordinates of the point P must satisfy this equation number 3, and therefore we put this expression of alpha and beta in place of x and y in this equation number 3, and we ultimately get this kind of expression. And finally we put the values of alpha and beta, already we have computed over here. So if we put the values of alpha and beta, we will get this type of relation. And this is the condition under which the given straight lines become conjugate to each other. As per the question, we have to find out the condition under which these two straight lines are conjugate to each other. Okay, these two straight lines should be conjugate to each other. So this is the condition under which these two straight lines should be conjugate to each other. So in this way we compute the conjugate lines. And similarly, if two other curves are given, and then also you can compute the conjugate lines with respect to those curves. I am not going to show you those results. You can go through this kind of question. Suppose this kind of question number 9. Suppose in place of this kind of curve, ax square plus twice hxy plus by square is equal to 1. Another kind of a circle is sometimes given, sometimes a parabola is given. The same kind of questions are there. So these are a few examples from poles and polars. Now let's get back to the chapter that is actually the main chapter, the general equation of second degree. So now I am going to discuss diameter and conjugate diameter. What are these? Suppose, let me show you by considering the example of an ellipse. We know that diameter is generally defined in case of circle. Got it? That is a general convention so far we have studied in mathematics up to school level. But now we can define, or we can extend this idea of diameter to other curves as well. It may be parabola, it may be hyperbola, it may be any ellipse as well. So what is the observation regarding the diameter? You see, suppose we have a circle. I am trying to start the points or the observations from the circle. That is actually the standard result you know about diameter. Generally, what is diameter? Diameter is the largest chord, you can say, or a chord passing through the center, like this. Now it has another property, and that is the main property for defining the diameter. What is the property? The property is that if you draw any this kind of chords, say this kind of chords. These are all parallel chords. I am drawing all these parallel chords, and it is the property that the diameter, this diameter line, this diameter line, it has the property that this diameter line always bisecting all these parallel chords. And that is the main property that is taken as the definition for the other curves. What I am trying to say, let me show you by an ellipse. Suppose we consider an ellipse, this black curve, say this is an ellipse, and we consider a parallel diameters, parallel chords, different kind of parallel chords. You see these lines are all parallel to each other. These lines are all parallel to each other, these red lines. Got it? And if we draw these parallel lines, if we draw all these parallel lines, then you will observe that the middlemost point of all these parallel lines, these middlemost points of all these parallel lines is passing through a straight line. Okay, and we shall prove this result. We shall before defining the formal definition of diameter, we shall prove this the equation of this kind of straight line, how to find out the equation of this kind of straight line. And what is this? These are actually, you see, these points are actually the middlemost points of all these chords. Okay, if you consider any chord, find the length and the middlemost point. If you want to find out, then you will observe that all these middlemost points will ultimately lie on a straight line. Got it? This kind of blue lines will be actually the locus of this kind of middlemost points. And this middlemost point, this locus, actually the locus of this middlemost points, this locus is actually called the diameter of the ellipse with respect to this system of chord. Why with respect to this system of chords? Why with respect to this system of chords? Because if we change this system of chords a bit, if we change this system of chords, if we rotate this system of chord, in that case the position of diameter will change. Got it? If we rotate the this system of chords, then with this corresponding system, the position of diameter would also change. I shall prove all these results mathematically, one by one. Okay. So, and this kind of chords are actually, this kind of locus of the middle points, these are actually called the diameters. And in case of central conic like ellipse or hyperbola, these diameters always pass through a single these diameters always pass through the center of this kind of central conic. It may be an ellipse, it may be an hyperbola. But in case of parabola, a diameter is always a straight line parallel to the axis of the parabola. We shall prove all these results one by one. But before that, we need to find out the result, that what would be the locus of these middlemost points. Okay, so and in order to find out this result, the equation of this kind of diameter, we are firstly trying to compute the locus of, not locus, rather I would rather say we shall try to compute the chord with respect to the middle point. That means if the middle point is known, all right, if this middle point, suppose if this middle point is known, then what would be the equation of this chord? All right, if this middle point, the coordinate of this middle point is known to us, then how to find out the equation of this chord, that I shall first discuss, and after that, after that discussion only, we will be able to find out the equation of this diameter. So these two concepts are actually related to each other. Clear? Now, is it clear what I tried to mention? Do you have any question? Then if it is clear to you, then I would go to the deduction portion. Is it clear what I tried to say? ব্যাপারটা clear হলো কি?
Yes, sir.
Clear? Okay. So let's go to the deduction part. So the chord with respect to the middle point, that actually is written in its previous section. Chord in terms of the middle point. So chord in terms of middle point, let me draw the picture for you. Suppose we have a, I'm drawing the picture over here. We have a curve S is equal to 0. And a straight line written in this form, x minus alpha by L, y minus beta by M is equal to R. I discussed all this in my first lecture, probably first or second lecture. So L would be cos of theta, M would be is equal to sine of theta, and in that case R would be the distance of any point x comma y from the fixed point alpha comma beta on the straight line. So suppose this is a conic, and suppose we have a straight line. All right, and suppose this point it's not clear at all. Suppose this kind of point over here, this kind of point is the middlemost point over here. Let us denote this point by P. Okay, and this straight line P means having the coordinates alpha comma beta. Suppose P point has the coordinates alpha comma beta, this kind of coordinate fixed point, having coordinates alpha comma beta. Okay, and we know that if this is the point, say capital A point, and this is suppose another point capital B, and suppose these two distances, this distance is equal to R1, okay, and this distance is equal to R2. You see, if these are the distances R1 and R2, then R1 and R2 will be obtained by putting this the expression of x and y from this equation of the straight line on this equation of the curve, and then ultimately we will get this kind of equation. Ultimately we will get this kind of equation involving r, a second degree equation involving r. This is the coefficient of r, and this would be the coefficient of uh, sorry, this is coefficient of r, this is coefficient of r square. Hmm. And if R1 is positive, then R2 should be negative, because A and B, these two points lie on two different sides of the point P, just similar to the positive x-axis and negative x-axis. If one direction is taken as the positive, in that case another direction should be taken as negative. So if R1 is positive, then R2 should be negative. Alright. And if suppose this point P is the middle point of the chord, in that case R1 should be is equal to minus R2. Got it? R1 should be is equal to minus R2. Both of these two, R1 and R2, will have same kind of magnitude, but their sign. That means if one is positive, another should be just opposite, that should be negative. If one is plus 5 unit, another should be minus 5 unit. Then only P will be the middlemost point of the chord AB. Got it? And if R1 is equal to minus R2, in that case you see R1 plus R2, that must be is equal to 0. And R1 plus R2, what is this? A R square plus y plus b r plus c is equal to 0. One root is R1 and another root is R2. That R1 plus R2 plus R2 is equal to minus of b by a, coefficient of r divided by coefficient of r square with a negative sign. So in this case, if by chance, as per the question, R1 plus R2 becomes is equal to 0, R1 plus R2 becomes is equal to 0, what does it mean? It means that B should be is equal to 0. The coefficient of R, this expression, should be is equal to 0. R1 plus R2 can be computed by the result that would be actually the coefficient of R divided by the coefficient of r square with a negative sign. That would be is equal to R1 plus R2. So if R1 plus R2 is equal to 0, then the numerator, that is actually the coefficient of R, must be is equal to 0, and that's what they have written over here. This is actually the coefficient of R is equal to 0. Here I am saying again that if R1 plus R2 becomes is equal to 0, then R1 plus R2, that value should be is equal to the coefficient of R divided by coefficient of R square with a negative sign, minus b by a formula. And therefore, as because this R1 plus R2 becomes is equal to 0, therefore only this numerator must be is equal to 0, that they have taken over here, that this numerator is equal to 0. Alright. Therefore, as because this numerator is equal to 0, we now eliminate L and M. Over here we have two unknown quantities. One is this L and another is this M. So if we compute L from the first and third ratio and compute M from the second and third ratio, in that case we can say we can eliminate L and M. Actually, in place of L, we shall have L is equal to x minus alpha divided by r, and M is equal to y minus beta divided by r. But on the right hand side we have 0, therefore divided by r, division by r, it does not have any effect at all, so we can omit this division by r. And afterwards, if we arrange these two expressions, then we will get the result this left hand side, is actually the expression of t. If you look at this left hand side, would be the expression of t, and this right hand side, would be the expression of s1, the notation that I have introduced in our earlier lectures. And in this book, in place of s1, they have introduced the notation s prime. Whatever notation you follow, ultimately the in symbolic fashion, the equation would be t is equal to s1 or t is equal to s prime. Okay, so the equation of the chord with respect to the middle point would be t is equal to s1 or t is equal to s prime. That is the equation of the chord with respect to the middle point. So to finish this class, let me complete the definition of this diameter, and one more related definition is the conjugate diameter. Hmm. Today I'll just introduce the definition only, and hopefully in the next class I will introduce the. Okay, let me first introduce the definition, because the computation is a matter of two line only. Hmm. So over here, this is the suppose this kind of equation. We have a system of parallel chords, and clearly that all these chords, the middle, we know how to find out the equation of a chord with respect to the middle point. Hmm? And suppose this kind of equation, let me show you over here whether it is possible or not. Let me check. um, just a minute. mm, hmm. Yes, it is possible. All right, suppose we have a we have an ellipse. All right, so let's start with the equation of an ellipse. Hmm. X square by a square plus y square by b square, hmm, is equal to 1. And suppose the parallel chords parallel chords have the equations like y is equal to mx plus c. You see, as because these chords are parallel, all these chords will have the same gradient m. All right, as because they are parallel, only the value of C will change. C may be C0 for one chord, C may be C2 for another chord, C3, C4, and so on. So for different values of C, we will get different straight lines, and these straight lines are parallel. Hmm. So we can say these straight lines are parallel. These chords are parallel to the straight lines, to the straight line y is equal to mx, hmm, where c is a parameter. That means we will get different values of this c, and for different values of c we will get different parallel chords. All these chords should be parallel to the straight line y is equal to mx plus c. And we want to find out the diameter we want to find out the diameter corresponding to this system of parallel chords. This system, we call them system. Altogether there are infinite number of chords parallel to the straight line y is equal to mx plus y is equal to mx. Okay, there are infinite number of such straight lines parallel to y is equal to mx, and all these straight lines are altogether collectively are called system of this is collectively called system of parallel chords. Hmm. We want to find out the diameter of this system of parallel chords, diameter of this ellipse, of course. Diameter of this ellipse. Hmm. Okay, corresponding to this system of parallel chords. Now, how to find out the ellipse, diameter of the ellipse? Suppose P is any arbitrary point on this chord. Okay, suppose this kind of point, I don't know whether it is possible to draw. Yes, it is possible to draw here. Suppose this is a point. um, Computer is disturbing. Just a minute. Is somehow not responding. Anyway, so let's check. No, it is not responding. Yes, yes, yes. Hmm. Suppose this is the point P, this black dot. Got it? Suppose this black dot is the point P, and let P alpha comma beta, let P alpha comma beta be a point, be the middle point, a point now be the middle point of a chord. Then the equation of the chord with respect to this middle point is, what would be the equation? T is equal to S1 formula. T is equal to S1 or T is equal to S prime formula. Now what is capital S over here? This is the given curve. So minus 1 is equal to 0. If we put this minus 1 is equal to 0, then this would be the expression of capital S. Alright. And at the point P, what would be the expression of T? T would have the expression like this. Let me copy and paste this expression. So x square will be replaced by x into alpha. This y square will be replaced by y into beta. So this would be the expression of S. And what would be the expression of S1 or S prime, whatever you call S prime at the point alpha comma beta? So x would be replaced by alpha. So alpha square by a square plus y would be replaced by beta. So beta square by b square minus 1 would be the equation of this S1. Therefore, T is equal to S1 formula. Let me copy these two expressions. T is equal to S1. So T is equal to S1 formula would mean that this is the expression of T, and this would be the expression of S1. So T is equal to S1 means we will get this kind of equation. And from this equation, if we further delete this minus 1 on both from both sides, so this would be the equation of the chord with respect to the middle point. Got it? Equation of the chord with respect to the middle point. Now its gradient. Its gradient is what would be the gradient of this expression of this straight line? The gradient of this straight line, you see, that would be actually the coefficient of x is equal to is uh, alpha by a square, and gradient would be this expression divided by beta, and over here beta b square with a negative sign. Its gradient, so let us call it m1. So m1 would be is equal to minus of this kind of expression. Hmm. The gradient of this straight line, what is this? This is actually one such straight line, this kind of straight line whose middle point is the this dotted line. Hmm. So we are actually trying to find out the equation of this chord, and we know that all these chords are parallel to which straight line? Parallel to this straight line y is equal to mx, and therefore there all such straight lines must have the gradient equal to small m. Okay, and therefore this gradient should also be is equal to small m. Got it? This gradient should also be equal to small m, and if we consider this expression, in that case you will see this expression can be written as beta is equal to minus of beta is equal to minus of b square by a square into alpha. So beta would be beta is equal to minus b square by a square into alpha. Therefore, so we can say the locus of the point P. What is the locus of the point P? Locus of the point P is actually this kind of diameter, the this kind of blue straight lines. Locus of the point P is actually the diameter. So locus of the point P, or the equation of the diameter. The equation of the diameter would be actually beta should be replaced by y and alpha should be replaced by x. So in this fashion we will be able to find out the equation of this kind of diameters. So if it is given this kind of parallel straight lines, then from that parallel straight line we can identify their gradient m. Got it? And from that gradient m, by this kind of mechanism we will be able to find out the equation of the diameter. Over here, just I would like to say that one property of diameter that I should mention. I'm not going to the proof all these diameters. I would just simply say that you please go through the different kind of curves. And just for example, I have shown you this ellipse, and this straight line that I forgot to mention. Hmm. This straight line, one straight line is y is equal to this kind of minus b square by a square into x. Hmm. And another straight line is y is equal to mx. Got it? These two straight lines, y is equal to mx, would be a straight line parallel to the system of chords and passing through the center. This kind of straight line, these kind of straight lines are actually called conjugate diameters. You can simply consider this kind of parallel lines. Over here you can also consider this kind of parallel lines. All right, this kind of parallel lines, you see, if you consider the second system of parallel chords, if you consider this second system of parallel chords, got it, then this straight line would be the diameter of this second system of parallel chords. Clear? Then this second system of parallel chords, with respect to this second system of parallel chords, this straight line would be the diameter. And this kind of diameters, where one diameter is parallel to the second system of parallel chords, these two kind of diameters are actually called conjugate diameters. And the conjugate diameters has the property that if we consider the parallel chords, say if you consider two parallel chords um, parallel to this red straight lines, these are the two parallel chords. Then these two parallel chords, which will simply touch these two parallel lines, which would simply touch the ellipse. And similarly, with respect to this diameter, this blue line, if we consider two more straight lines at these two endpoints, okay, at the endpoint of these two diameters, okay, at the endpoint of these two diameters, then they will all be tangent at all these 4 points, and ultimately they would form a parallelogram like this. And over here you can simply find out where is the picture in this picture. Where is the picture? This is the picture of the this result I proved over here. This result I proved over here. And I'm not going to the detailed discussion because formally this is not known, this is not given in your syllabus. So these two are actually the examples of conjugate diameters. And if suppose we know that the point on an ellipse, any point like P on an ellipse can be written in this way: uh, a cos of theta. Okay, a cos theta, b sin theta. Any point on an ellipse can be written in this fashion. So if these two lines P prime and D prime, if these two are conjugate to each other, then if we know this coordinate theta, then we can find out the corresponding parameter of the point D, then the parameter for the point P prime and the parameter for the point D prime as well. Suppose this equation, this point D has this kind of expression: a cos of theta 1, and b sine of theta 1, then theta 1. Then one can prove that this theta 1 is equal to theta plus pi by 2. Okay, theta 1 is equal to theta plus pi by 2. If suppose in place of theta 1 we have theta 2 for this prime p prime, then this theta 2 would be is equal to theta plus pi only. And suppose in place of theta 2, if we have theta 3 in case of the point D prime, then one can prove that theta 3 is equal to theta plus 3 pi by 2. Okay, 3 pi by 2. So these are the short brief results related to diameters and conjugate diameter that you need to remember. I am not saying to remember all the results, just few important results I have discussed over here. It is not possible for me to discuss the entire chapter, and even it is not required for you. Okay, so this much I wanted to discuss in this class. So you please go through these results only, and that would be sufficient for your exam. And remember this result: m prime, one number is m. In case of n prime I have discussed m1. You see this over here from this relation, this is our, if we call it, this is m prime. If this is written in this way, you see, if this is written as y is equal to y is equal to m into m prime into x, then what is m prime? Then m prime is equal to minus b by a, and for conjugate diameter we shall have the result that m prime is equal to this minus b by a. This is the condition under which two straight lines y is equal to mx and y is equal to m prime x become conjugate to each other for an ellipse. So if possible, try to remember these results. That's all. Because it is not possible to remember all the results. You just please try to remember this kind of results. In case of ellipse, we have this result, and in case of hyperbola, we have, in place of minus sign, we have plus b square by a square. Okay. So that's all for today. Thank you for being with me in this class.